Okay. Okay. So this is the last hour of this first day. Um, I I I have one exercise which is going to not going to be able to do the whole thing. So because there's not enough time. So I'll start with that. But then there's I mean, hopefully one can follow the slides and more or less by trial and error can practice. In any case, the solution will be uploaded to the GitHub of the third exercise. But before I move on, I promised I'd take any questions you have now. Don't worry about time. If you have anything I want to say again about what's already been covered, then please ask me to. No. No? Okay, good. So let me move on. Okay, so the last exercise that we will see is a matrix vector multiplication. So so assuming, so this is the operation. Oh, maybe I should make this first. Yeah. So assuming y and x are one-dimensional and a is two-dimensional, then this is a matrix, so-called matrix vector multiplication. In a general case, a will not be square, and yeah, and so if a has dimensions m times n, then necessarily x needs to have dimensions n, and y needs to have dimensions m. Okay, if I write this out in just a big loop, then for each of the elements of y, the result is this sum, right? So is the sum over the j chord index, so the fastest running index of a and the index j. So if I just write this in a pseudo C code, then this will look like this. So as we said, so this is this loop is what's written here in math notation, where I'm running over j to fill up the elements of y. And then of course you have an outer loop over y, right? So it's double loop. So the number of operations you're doing here is 2 per line, and you have n times m of this line, so you can figure out that the number of operations here is 2 times n times m. And the memory that you need to read and write, assuming everything is not in cache, blah, 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 is that you need to read x once, read all elements of a once, and you need to write y once, right? Okay. Okay, so this, I mean, yeah, okay. So in C, you can make arrays look like this, but it's much more common to use one-dimensional arrays, even, and then wrap around their indices to make, sort of two-dimensional arrays. So in C, it's much more common to see arrays written like this. Okay. So you take the single index, you take the two indices, sorry, I and j, and you convert it into a single index. So that's basically the kernel that we want to implement. Okay, so I guess you're familiar by now with the procedure. If I just copy exercise 3, then there's this matvec.ku file, which I will go through with you right now. even though it's highlighting, let's make this a bit bigger. So the inputs are m and n, right? M and n define the dimensions, as I said, of A, but then they also constrain the dimensions of X and Y, right? Because they have to have the correct shapes for this to be a valid matrix vector multiplication. This should look familiar to you by now. This should look familiar to you by now. This you should know. And the new thing we find is AX. AX takes takes 5 arguments, the dimensions, and then it takes Y, A, and X. And this is exactly what I've written on the slide with a pragma on top to parallelize the outer loop. Okay. Okay, so I probably don't need to go through all of this. I'm just initializing the array here. And then I'm computing AX twice. Once I'm storing the result in Y0, and the other time I'm storing it in Y1. And guess what? At the end, I am comparing the two to see if they're the same. And yeah. Okay. So the idea is to turn this into the GPU part, right? Done it twice already, so let's see. Okay, so now this is a bit of this is not as straightforward as before, right? So we need to make some decision now. What we distribute threads, what is each thread responsible for? So we're going to start simple. First of all, yeah, maybe I should just go through the motions here, just compile this for the just CPU only for now. Oh no, like this, and I'll run it. Let me see what I have on the slide. Put the dimensions I have. Okay, 4096 and 8192. 4096, 8192. Okay. Yes. Okay. So that's the performance we get on the CPU, and that will be sort of our baseline to compare also the GPU performance. So as I was saying, we have some choices to make here. We want to put this on the GPU. Okay, I'm gonna. Okay, well, if you have the slides, maybe there's no point if Huston knew what we could. So let's just go to. So the first thing I posit, the most easiest thing to do is to have each thread compute one element of Y. Okay. So this is probably the fastest thing you can put together. If I were to just give you this and tell you, I don't care how optimal it is, just make it work, okay? Because this will require actually no shared memory to begin with. So if each thread computes one element of Y, then let me go. Yeah. So basically, each thread is doing this loop, right? And so there is no, I mean, we'll talk a bit later about how you can use shared memory, but you could just do this you will just do this to begin with without any shape memory. Okay. So for the interest of time, let's just go through this together, shall we? Let me just start doing this by so we will first, okay, sorry. So we will first, include the CUDA runtime header file. Good. Then we need our familiar by now GPU allocate function. And I will save, as I said, okay. So there, I'm just putting it up there. So I will save the kernel version, the GPU version of the actual matrix vector multiplication for last. So for now, we go down to main. Okay, and we, what we want to do is first create device pointers for X. So X is N, right? Y is M. And A is N times N. Okay. Okay, and just shout out which arrays do I need to copy to the GPU? I'll give you a hint. It's just two of these that I need to copy to the GPU. So I'll just fill in here until somebody can be brave enough to shout the answer. I'll just fill in these arguments here. And I think anything else I write here will give it away. Somebody wants to speak.
A and X.
Thank you. A and X. Very good. X is N. Yes, N. Okay, this will turn into GPU AX. And let's talk about the number of threads later. The arguments will be M, N, dy, dA, dx. And let's make sure we synchronize so that we don't measure the wrong time. And we need to copy back Y. Put it into one. So there is dy. This size is M, and then I'm copying. Awesome. Don't need this. Don't need this. Okay. Right. So we go up here. And let's write, wrong way. Let's write the GPU kernel using not open. Okay, so global GPU, oops, GPU AX. None of that. Okay, so we said that for this first iteration, wrong choice of words. For this first version of this operation, so the simplest case, then we will have each thread compute one element of Y. The number of elements of Y is M, right? So M, this one. So we need to distribute over that index. So let's do our familiar dance here, where you have int items equals thread index dot x, int I block equals block ID x, and what was the other one? Int and thread equals block dim, yeah, block dim x, and that way we can figure out the index, the global index, as I thread plus n threads times IBLK. So this now, this should be sort of hiding, or should replace, this IDX should replace the loop over I. Okay. Okay. IDX to the loop over I. Yes. Yeah. Okay. So this is so okay, what I'm going to do now is, as far as I can tell, not really necessary anymore on newer versions of GPUs. But it used to be that doing this kind of thing would actually access Y repeatedly. And so you would, in such tutorials, you would be advised to have some temporary variable. Oops, what am I doing? Something like this. And sum it up here. But I think this is, well, there are still GPUs out there that would benefit from something like this. So, okay. Yeah, let's try this out. Oh, wait, I still haven't done the number of threads, but now it should be clear. We said we're parallelizing M. So we have some number of threads here. Let's say 512. And so now we use M over N thread blocks and N thread threads per block. Okay, let's see how many compilation errors I get this time. Surprising. Okay. That looks okay to me. Performance looks bad. But we did say this is a first version. Okay, any questions up to here? No, good. Okay, so what can we optimize? There's several bad things going on here. If we just look at this picture, stuck to this. Oh, okay. Okay. So this represents a block now, right? So in this small problem size that I've drawn here, the block is this. The block is basically length 4, so n threads is 4 in this case. Just so that it's easier to show. And so each different shade of orange here represents different thread in that block. And so what are we doing? So, okay, so as far as A is concerned, this is pretty decent. So each thread is accessing different row of A. That's okay. So the first thread is accessing this row, the second thread accessing the slightly lighter orange row, the other one, etc. So that's not necessarily inefficient, but all these threads are accessing the same elements of X, right? Because they need the same column, the same single column of X to do the matrix vector multiplication. So you have all these threads, they're all reading X again and again. Okay, so we can't really avoid this for different blocks, right? So, you know, this what I'm showing here is sort of the middle block, but of course, also the threads on this block need to read this memory, right? All these elements. Also, this block and also the 4 threads in the final block need to read the same elements. So between different blocks, this is sort of unavoidable because we can't really control when each block runs. But at least for the threads that are in the same block, maybe we can do something so that at least those threads do not read the elements of X multiple times, okay, as a first step. Good. The problem is that in order to allow for X to be arbitrarily large, right? In order to not constrain the size of X, we don't really have enough shared memory to store. We can't guarantee that we will have enough shared memory to store all elements of X. So we have to do this piecewise, okay? We have to have a small amount of shared memory where we will copy the elements of X in and then do partially the matrix vector multiplication for that small piece of X, and then stop doing the matrix vector multiplication, copy new elements, sorry, I'm pointing at the wrong thing, copy the new elements of X into the shared array, and then continue the matrix vector, etc. Okay, so we need to do it in steps. Why? Because we don't have enough shared memory to fill the whole X at once, so we have to do it piece by piece. That's just this is what I'm trying to show here. Okay, so if you just look at, right, so just look at this bit here. So if XB is the array, is the small array that will hold the subset of the elements of X, right? And in this case, XB will be as big as the number of threads that we have, right? Doesn't have to be, but this is how we're implementing it here. So we have 4 threads in this very simple case. So we have an XB, which is just 4 elements big. And so what we want to do is this procedure, which I will describe. Take the first 4 elements of X, put them in XB, and then have all the threads do little matrix vector multiplication, right? Little matrix vector multiplication. This little matrix is going to be 4 by 4, okay? Okay, once you've done that, then you have the partial result for y, right? And then you move on to the next 4 elements of x. So you copy those 4 elements into the same shared array you had before. You're overwriting the elements you had before. And then you're doing this the second 4x4 matrix times the 4 element vector here. And you're accumulating that result to the other 4 elements of y you had before. So you do this in the stepwise process. What do you achieve? Well, at least what you achieve is at least within this block of 4 threads, you only needed to read every element of x once. Okay, so you save the extra 3 reads in this case, 3 being the number of threads minus 1. But of course, you can imagine that if you go to much larger block sizes like the ones we used, like 1024, then you're reducing the reads by that factor. Okay, I hope that was clear. It's written here in words, in text maybe. So we need to split the matrix vector multiplication of the block into these steps that I just described. And okay, I mean, I would normally give people here 20 minutes to do it, but that means that we're already out of time. So let's let's just do this together. So what do we want to do? So how to think about this? So excuse me, I'm just retrieving a bit some notes here. So just remember that you don't need to do anything in the invocation here. So you will still use the same number of threads per block, right? It's just that inside the kernel, the procedure will change, right? So we're not changing that. So I will just put an underscore here, or call this 0, right? Just keep it in there so that we can look at it. But what I really want to do, okay, so I'm just saving this as 0 here, right? But what I really want to do is now implement this new one here. Okay. So first of all, what do we need? Well, we need what I said we would need is a new small array that will store the elements of x. And this is a shared array. So shared, it's got to be float. And I'll call it xb to be consistent with my slides. And here will be max threads. So the biggest this array, I mean, okay. The way we're going to do this algorithm, at least, is that the biggest that this can be is the number of threads, right? And okay, so I just have to define somewhere the maximum number of threads. Just define here max. It's yeah. So we have our array now, and okay. So what does this mean to do this? So I mean, what I described is basically to what was before a loop of this j index that was going from 0 to n-1, right? We're going to break up this j into basically 2 indices. So the inner j will go from 0 to 4, or from 0 to n thread, 0 to n thread, 0 to n thread, 0 to n thread. And the outer j will tell you in which of these block X's you are, right? So you're breaking up the single J that went from 0 to n, you're breaking it up into a little j that is going over the threads and a big J that is telling you in which part of this red shaded region you're actually operating on. So let's, yeah, so I'll call those J1. So that will be J1. So J1 will go, okay, I don't necessarily have to do it like this, right? I can go from 0 to n over, well, the block DMX is just 10 threads. Okay, so this J1 is, again, I'm just repeating here, is just telling you, so when J1 is 0, then it means that I'm inside, I'm going to do, it means that I'm at the outer iteration, which is going to do this matrix times the first 4 elements. When J1 increments, it becomes NTHR, right? So it goes 0 NTHR, 2 NTHR, 3 NTHR, 4 NTHR, up to n. So when this increments to the next, then it means that I'm actually working on this one, which is going to multiply by the second group of n thread. Okay, so that's what this J1 means. And then the inner loop will be what I call J0. And that will just go from 0 to n thread incremented by 1. Okay, so that J0 now counts which thread I am inside here. Am I 0, 1, 2, or 3? Am I 0, 1, 2, or 3? Am I 0, 1, 2, or 3, right? And then J1, as we said, counts the outer iterations. Okay, so now I've set up the loops, but that's not, of course, sufficient, right? So I need to do stuff between the loops and inside the inner loop. Let's see what I need to do. Okay. How do we go about this? Okay, so first of all, every time this increments, J1 increments, I need to fill in X with the new elements, correct? So this is where I need to fill in XB. Okay. Okay, and XB will always be I thread here, right? Because XB has the number of elements are the number of threads. But every time J changes, right, I need to change the location in the global X array that I read from. And I'll just write this. So this will be J1 plus I. Right? Okay. So when J1 is 0, it means that the first 4 elements here will be put in the first 4 elements here. But when J1 increments and becomes n thread, that means that you start from n threads and copy these into the elements of XP. Okay. Okay. I think that's okay. All right. So here I need now I will go down and inside this loop, where in this loop I will do the little matrix times little vector multiplication, little matrix times little vector. But before I do that, I need to make sure that all the threads have written to this shared array before I start doing multiplication. So I need to sync threads. I need to make sure here that, for example, the first thread will not start doing its multiplication before the last thread has actually copied the data into XP, right? Because that would be wrong. So, you know, in a very asynchronous scenario, which is possible, right? When these threads just run and you're not sure which one runs faster than the other, it could be that one of the threads is still copying the data, so it's still doing this operation, right? So one of the threads is doing that while another thread has gone in and started doing this loop. And so it might actually try to read from XP an element that hasn't been written yet. But this sync threads ensures that the setting of XP has finished before you move on. Okay, so here now, all we do is the little matrix times vector multiplication. I'm calling it little because it's, n threads times n threads, right? Rather than the big A. So it's just this little a times n threads. Okay, so again, which row am I on? That's just the global index of the thread, right? That's the row. Yeah, that's the row that I want. So so remember, J1 jumps by n thread every time. So that means that what was before J is now J0 plus J1, right? Just because of the way that I set up J1. J happens to be just J0 plus J1. You don't believe me? Okay. When J1 is in its first, not in the 0th, but in the next iteration, then J1 will be n thread. And then J0 will go from 0 up to n thread. So that means that the global J will go from NTHR up to 2 NTHR minus 1. And then in the next, it'll go from 2 NTHR to 3 NTHR minus 1. Okay, so just as we want J to be. Okay, we have J. Okay, all it's left to do is to accumulate the row, which is IDX times n, like before, plus J. And now you don't have X anymore, but you have XB, right? Which you're reading from. And XB now is the little array. So you use the little j, right? The inner j. Okay, so now I don't need this anymore. Okay. You need another sync threads. Okay, that might need some thought why, but basically you need to make sure that everybody has finished using XP before you go into the next iteration and start filling XP again, right? Now, you don't need it in the last iteration. So I could say if J1 equals to n minus 1, I guess. So I could do something like that, but presumably we have enough J's. Maybe I should do that. Okay, this is I'm going off script again because I didn't think to do this when I was setting this up. So if J1 is not equal to so if it's this needs to be if it's smaller than n minus n thread, I guess. I can't think of it. It's too late in the day. There is one iteration where this doesn't have to be done, and I need to figure out what the last iteration is here, but whatever. Okay, I think we can try this out now. Yeah. Let's see. Yeah. Okay. So this Okay. Okay, so what was I going to say? Okay, so this now needs a bit more tuning, like the number of threads, etc. But in general, you will see for yourselves that this doesn't become extremely more efficient. Okay, than what we had before. Okay. Yeah. No, something is wrong here because this is very small. Okay. Anyway, so yeah, so there's some tuning there for the number of threads per block, etc. So some cases, the naive version will actually be faster than this presumably optimized version we did here. Sometimes this optimized version will be better. It depends on the shapes of the arrays, sorry, as well as the number of threads per block. But in general, this is a kind of kernel, I should say, this matrix vector, where it's difficult to get close to the GPU peak performance. So in the next example, I will just go through it briefly, but I won't actually implement it because it'll take too long to do that and we'll be out of time. But in the next one, you can put the solution up in the next days, and you can also go through the slides. And if you have any questions, you can ask me. Basically, in the next one, what you do is you use a shared array, both for X and for the little a. Okay. And right. And now each thread is not just filling in a given element of Y, but each thread is responsible for computing, for filling in, let's say, for filling in the elements of this little a. Okay, so you have a group of threads which have an ny, which are two-dimensional now. You were using a two-dimensional grid block. And we're using the 2 dimensions of the threads to fill in the little a. Okay. And then only some of those threads are used to do the little matrix vector multiplication. Okay. And then you have even more ways to optimize and tune this because now you have 2 dimensions of threads to go over. Okay. So when you do all this, right, and you spend a day debugging, then you will find out again that the performance is not that much better than what we achieved before. But this is just to say, this is just to show a bit what kind of motions you should you typically go through when you try to optimize such kernels for the GPU. Okay. Okay, so this was sort of a more advanced step that I was going to do if there was enough time to explain it. The last thing is to see a bit, okay, so what if we just gave this to a dedicated CUDA library to do this operation, right? So CUDA implements a set of blast routines. It also implements exactly what we're trying to do here. So but let's use it, right? Let's not write our own GPU_AX function. Let's use cuBLAS. So you can look at how you invoke this function here. I'm giving you here the name. But let's see what we can do. So the first thing is we should say that this function cuBLAS sgmv is actually doing a more general thing. So it's doing the AX that we want, but it's also adding back Y, and it's also can multiply each of these with a scalar number if you want, right? So we want this function, but with beta set to 0 and with alpha set to 1. So yes, in our case, we need this, and okay, I mean, there's some smarts inside the library that, of course, will skip this operation if it sees the beta is 0. So it won't do unnecessary memory accesses, etc. Okay, so this is how you would call it here. So where this handle is just, so yeah, well, let me go through this. So N and M, you know what they are. They're just the dimensions of A. Alpha, we give it 1, and beta, we give it 0. DA, DX are the device pointers, of course. And okay, and then this is just to tell it that A will be the transpose of what it expects, because cuBLAS expects matrices in so-called Fortran order. So it expects matrices where whichever is, so what is the fastest index is C should be the slowest index in this Fortran order. So you're just telling it that what I'm giving you is the A transpose. Okay. And handle is just something you pass, which you initialize like this, create handle, and it's just, something you carry around which contains some information for cuBLAS. Okay, so all this is to say that even if you use CUDA's cuBLAS, for some shapes like the one we were trying, the performance is more or less what you already get. Okay. So actually, I managed to come here with enough time to hear questions, but I will also put another version of the code online that you, if you like, you can see, which implements this using cuBLAS, and just check for yourselves that the timing is very similar to what we get in our sort of handwritten code. Yeah. Okay. Yeah. So that's all I had for today. Sorry that we couldn't spend more time on say the practical, letting you do some of these yourselves, but hopefully you can do them offline and come back to me if you have any questions. But of course, if you have any questions now, we still have some minutes to answer.
Yeah, sorry.
Mm-hmm.
Would it make any sense if we used, like, for each block an entire column of A and only one element of B to compute separate, let's say, partial Y's, and then add them, accumulate them, vectors?
Yeah, so let me understand what you're suggesting. Can you say it again? So each.
So let's say we just transpose matrix A.
Yes.
And we just use, let's say, for each only one element of X, sorry. So you get a vector, like you multiply a vector with an element. So the vector you get, if you add it with the other vectors you're going to calculate, you get Y. So you transpose the order of summation.
Great. So let me just say this then, just so to make sure I understood. So these elements here all get multiplied with this first element here. Okay.
Yep.
And then, okay, here we have 12. Okay, so we have 12. So M is 12 basically, right? Because it's 4, 4, 4. So you would have 12 numbers, which you would put into the 12 elements of Y. And then you would do the same for the second column of A. Multiply that with the second element of X. And then those 12 numbers would be added to Y, right? And then you go to third. This is what you're suggesting, correct?
Yeah, basically to avoid like accessing many elements of X and the need for synchronizations in between the matrix vector multiplications.
Right, yeah. So what is a block in this case?
The entire column of A, I would say, yeah, the entire column of A.
Okay, so your block is, so each thread in a block. Okay, so, well, we might not have enough threads for the whole column of A, but I mean, maybe this is a block. So it does this for the first element of X, and then this is a block, right? And it does it with the element of X, and then this is a block. And maybe you can have a lot of blocks like this, and each block takes
Only one element.
Yeah. Okay. So here's the thing. So you don't know which order the blocks will be executed, right? But somehow you need to accumulate their results into Y. Okay. So at some point, you need to serialize them in order to add to Y. So this is actually one of the tricky things to do on the GPU. For example, this is very similar to when you want to do a reduction. Okay. So let's say, I mean, a simpler way to see it, what if you have just a dot product? So you have you just want to do one row times one column, which results in a scalar number, right? So there's all sorts of algorithms of how to do this on the GPU. The main problem being that if you split this up into multiple blocks, then there's no way for the different blocks to store data, right, to accumulate data between them, other than storing them into global memory. So at some point, the block needs to go to global memory and write its result, and then the other block has to go to global memory to read that result so that it accumulate on it and put it back, right? And you also need to make this atomic somehow. So you also need to make sure that when one block is accumulating, another block is not accumulating at the same time. So that is, so what you're describing will run into this problem, I think, right? What you're describing will necessarily need to accumulate data between blocks. And it's not that this is not possible, right? It's possible to do, but usually that's the thing you want to avoid, because that requires some serialization or some atomic operations of blocks on global memory. Yeah, is it clear what I'm saying?
Yeah, I guess when you do, like, let's say when you break it up into smaller blocks, the A matrix, then you again have to serialize it somehow to accumulate all in the Y vector.
No, because this is, I mean, at least what I'm showing here, right? This all is done in the same block. So it's just that we broke it up in steps. I mean, if what you're describing is if what you are describing is to stay within a block. So this will be, I don't know, I'm just trying to figure out if there's something there. So this whole thing times this. No, that's not possible. You need to do the whole thing then. No, I don't know. I have to think about it. But it seems to me that you can't avoid, if you're going to change the order, you cannot avoid having to synchronize, having to accumulate across blocks. Maybe I'm not seeing it. I don't know. Maybe I have to think about that a bit. If you can work around it, but yeah. Okay. Anybody else? Or maybe the same question, or maybe the same, maybe we can, you want, maybe, I don't know. Another idea maybe? No? Okay, well, if there are no more questions, then feel free to try these and contact me even after the week. It's fine, right? You can still come to me with questions even after the training is done. Or if you have some other kind of similar question about GPUs, you know, we can try. I can try to answer it. But yeah, so the solutions will appear at some point within the week on the GitHub page in case you want to check your results. But other than that, thank you and hope you have a nice rest of the week. Okay. Thanks.
Thank you very much.
Giannis for being presented today.
Thank you.
Thank you everyone for joining, and remember that we carry on tomorrow at 10. Simone and Nikos will be your trainers tomorrow. See everyone tomorrow then. Bye-bye.
Thank you, Giannis.